So here's the thing. Welcome to the Build Different podcast.
Well,
Cool.
thank you.
Emphasis on build. With me, Sam Weiss, my brother David, and joining us today, Nathan Hoffer. Thanks for being here, Nathan.
Hello.
Yeah.
Okay, I have known Nate for, let's see, maybe like 15 years, something like that. We met in school.
Yeah.
I think you're probably about 2 years ahead of me. We were both studying mechanical engineering. I, as a sophomore or junior, got involved in a lab at Utah State University where Nate was helping to do the research and lead the development efforts there. And so I worked with Nate there for like 3.5 years. And we've become close friends over the years. He's working at Northrop Grumman, being a real engineer, and I'm doing all my pretend engineer stuff at startups. So
I would
I'm
not call
so-
that pretend
I'm
engineer.
so excited to have Nate here because he's a wealth of information. He's a systems engineer. And I think we're going to have a great discussion about
Hey,
space.
intro though. Nate, what does it mean to be a systems engineer? That seems so
Oh.
like generic to my mind.
Yeah.
What does it mean?
This is like systems engineering was never taught to me in school, and I had to learn it, in the lab and at Northrop Grumman. And I just gave a presentation about this for a job interview, and the way I simplify it is systems engineering is all about relationships. So you have customer needs, and you're building relationship between what the customer needs and what you're going to build, and then a relationship between what you build and how you verify that you met those customer needs. The other thing is a relationship between how the part fits in and affects the whole. So it's like interfaces. And then one thing that I don't think a lot of people hit on, but systems engineers are kind of the go-betweens between people who have the knowledge and people who need or the information. And so systems engineers typically help bridge the gap and help with communication issues, because we're supposed to be able to interpret process engineering and the program managers, the chief engineer, the project engineers, and even people on the floor, and help them all, and the design engineers, and help them talk the same language, because they typically get siloed and so focused on what they're doing that they have a hard time, expanding their view and just talking to each other. So it's kind of interesting.
Were you?
That's so cool.
You weren't originally hired as a systems engineer, were you?
No, I was, yeah.
You were.
Mm-hmm.
Was that like a thing? You were like, I want to go be a systems engineer, or was it like?
What the way it happened was, I've always loved mechanical and aerospace. I knew probably since I was like, I don't know, in kindergarten or something. Really early on, I knew it was either I'm going to be an astronaut, a pilot, or an engineer. And as I kept going, I was like, well,
you did not choose wisely. I mean, there's like, what happened with the astronaut thing? At least a pilot, and now you're a systems engineer. Come on.
Well, the pilot was, I wanted to be a fighter pilot, and at the time,
yes.
they were like, well, you got to have perfect vision, and obviously I don't. And I was like, and I couldn't get into the Air Force Academy. I wasn't competitive enough, I think is what our letter said. And the astronaut thing, I was like, I don't think I quite have the right temperament to handle that kind of stress. When I really thought about it.
There is time.
There's still time.
We're going to talk about this.
There's still
some
time.
super old astronauts up there. I don't know how they do it, but they're doing it. But yeah, just from the lab, I understood. I'm really good at the high level architecture, at bringing things together. And so I started looking for systems engineering jobs, because I knew I wasn't like a very good like design engineer, like very detailed, like for stress analysis or aerodynamics. Like I knew enough that I could understand it, but not enough to like really do it like Sam. So anyway, yeah, that's how that started. And when I first hired on, the guy was like, "You're perfect." Basically told me like on the spot, like, "Yeah, we'll definitely get you an offer tomorrow."
That is
That's
so
so
awesome.
cool.
Okay, you've been at Northrop now, like how long? 8 years?
A little over 7 years. It'll be 8 in March. 8 years.
That's awesome.
And I've been basically a systems engineer the whole time, uh, working various projects. My favorite is from the start to the end of development. I haven't really been like on the production side.
I think you've been involved in probably one of the coolest programs at Northrop, and that's the Smart Demo project. And I
Yeah.
want to hear more about that. If you can, maybe you can tell us more about what it
Yeah,
is,
yeah.
and then some of the things that you guys accomplished, because I think it's an incredible
I've
program.
never even no, I've never even heard of this. Is this secret? Like, can you talk about things that you work on?
Yeah, so this one they have recent posts about it on social media, and we're trying to actually make big noise about the successes we have. So Smart Demo is it's an internal research and development program. So and Northrop is huge. So this is specifically for solid rocket motors, which have been around, I don't know, like what, 70 years? I mean, they've
Long
been
time.
around for a long time. And solid rocket motors haven't changed very much at all. They've used different materials for like the case, and they've tweaked the propellant formulations over time. But there hasn't been like major innovations, I would say, on how they do it. And so there have been a couple of startups in the solid rocket motor arena for government stuff, and there's really only two big solid rocket motor producers. There's Aerojet Rocketdyne and Northrop Grumman, which used to be several other companies before they got gobbled up. And so those two usually went for every single contract, and it's usually Northrop gets stage 1, 2, Aerojet gets stage 3, or some permutation of that. But recently, there's been these new startups that are starting to get in there and get contracts, and so it was evident, at least to propulsion systems, we really need to be showing that we can react with speed, that we can become much cheaper on the development of a rocket motor and start to use new technology. So uh, the main focus there is to develop a solid rocket motor from conception to static test within a year, which is a very aggressive timeline because the traditional tooling, some of it takes upwards of a year just to get the part in. So if we're talking a steel mandrel, that's a forged part, and so that takes a long time first to design enough so that you can know what you need to get, and then to have it manufactured and machined. And
Okay, so pause
Why
for a
does
yeah,
second. Pause for a
go
second.
ahead.
Two questions.
hmm
Question number one is, what's like for a layperson, what what is the difference between a solid rocket and a liquid rocket,
Yeah.
or whatever the opposite is? I'm
hmm
guessing liquid.
Yeah.
And then
So
what is a mandrel?
okay. Yeah. Sorry. Good questions here. So solid rockets, think of a firework. It's literally packed. Usually, it's some kind of metal, aluminum, and then some sort of binder, and then an oxidizer. Think like um, fertilizer or other ammonias, and um, so that way the oxidizer, the oxygen, and the fuel are together, and they can burn basically in a vacuum. On a liquid
But
engine,
they don't shut up. You can't shut them
yeah,
off.
there's no real way to stop them. There's ways to shape the burn, the thrust that comes out by doing different things. Um, to the shape of what's called the grain, or that solid propellant. And then the comparison is a liquid engine. You have an oxidizer fuel. It's liquid, so like liquid oxygen, and then you have the fuel, which is either liquid hydrogen, kerosene, rocket RP1 rocket propellant, which is like a highly refined, not gasoline, ethanol or methanol, I think is what it is. Anyway, so the cool thing about solid rockets are they're ready to go at any time, and there's not a lot of moving parts. So in a liquid engine, you've got these turbo pumps, and it's a very complex startup system. You have to fuel it. You can't just have the fuel sitting there because the gases that are, or the liquid will start to boil off and pressurize and basically explode, right? And so they have to be at cryogenic temperatures all the time. And so if you're looking at something you need to launch at a moment's notice, like a missile or an interceptor, or you want something to be super cheap and very, very reliable, solid rockets is where it's at.
So when the space shuttle was going, the two things on the side, were those solid rockets or were those
Correct.
liquid?
Those are solid rocket boosters that we produce. Yeah.
Northrop Grumman produced them.
Yep. Yeah. Yeah. So Promontory is the place where they were manufactured in sections, and then they ship them by train to Florida, to the Kennedy Space Center, and then they stack them in the vertical assembly building and mate them to the core. And then the follow-on for the space shuttle is the Space Launch System, which has an extra segment, and they're made by us as well. And it's a similar design. They actually use the old shuttle cases, so the metal cases that they'd recover. Those are the same ones. They fish them out of the ocean and refurbish them, and that's what's going on that first Artemis mission and the second one coming up here in a couple months. Yeah.
Okay, wait.
Wow. Okay, so what's a mandrel? I need to know what a mandrel is.
Before we get to the mandrel, for completion, there is another type of rocket motor called a hybrid rocket motor.
Yes. A hybrid.
What?
That's the kind that Sam worked on.
I worked on that as an intern for a few months at Scaled Composites.
Was that vertical Virgin Galactic was doing this?
So the Spaceship 2 uses a hybrid, and for the hybrid, what you have is your propellant that's just the propellant, and then the oxidizer is in a pressurized tank, and you squirt the oxidizer through the propellant.
Yeah.
To get
the oxidizer is a liquid.
The oxidizer is a liquid, and the fuel is a solid. And what's cool about those is you can shut them off and throttle them, because you can adjust how much oxygen you allow into the motor, and you can shut off the oxidizer if you want.
But still reliable, still stable, still super safe.
It's more complex, less reliable. There's I don't know. They're not used very much.
Yeah.
It's like you
might say it's the worst of both worlds.
You can totally. There's like this, for what happened with Spaceship 2 was that it was like a solid rocket motor was not viable because they needed.
What is Spaceship 2? Tell what I don't even know what it is.
It's a space plane that does like a suborbital launch. So Scaled Composites back in the day won the X Prize for the first reusable commercial flight, and that was Spaceship 1. And then Spaceship 2 was the second version of that eventually Virgin Galactic took over for commercial space
so
flight.
Spaceship 2 was that huge that they took two Boeing 747s, bolted them together to carry this spaceship monstrosity into the air.
That's a different project.
Yeah,
related.
Strato launch.
Yeah. But
okay.
Anyways, so for Spaceship 2 and with Spaceship 1, the idea with the hybrid rocket is they could get some control for the throttle, shut it off if they need to, right? Because there are humans on board, and they could shut it off if they needed to. But it's not as complex as a liquid rocket. Anyways, solid.
Hold on. One more question. Which one has the best like thrust to weight characteristics?
Well, liquid are much better. You can get much higher. It's called ISP, which is just a measurement of how efficient, essentially,
Yeah.
the propulsion is. So solid rockets are really good at getting you a lot of thrust off the ground. Like if you watch Starship or a Falcon 9 or a Falcon Heavy or any liquid, they go relatively slow. They're like,
Yeah, totally slow. It's crazy slow.
especially Blue Origin's. Is it the New Glenn, the big one? I always
Yeah,
get
New
them
Glenn.
mixed up. It was really slow. It's like you're like, come on, buddy, get off.
Yeah.
If you watch the
What's
space
going on there?
shuttle, it just instantly like blasts
Yeah.
off,
The
and so
solid
you can get
boosters.
a lot more thrust instantly off of these versus the liquid. Liquid more
Oh, I
efficient.
get it. So the trade-off is liquid's more efficient, but it's not as instantaneous
Yeah.
as the solid rocket
Right.
boosters.
Yep.
Got it. Okay.
Yep.
All right. Thanks for. I mean, I'm not. Got to understand this stuff. So
Yeah, no problem.
sorry, Sam. Go ahead. Questions.
No, let's
wanted
we
to-
can. Though just we've got solid, we've got liquid, we've got hybrid, and now we can go to mandrel. What is the mandrel?
Yeah.
Because you
So,
did some really cool stuff on the mandrel tooling.
Yeah, this is some of the cool stuff. So a mandrel is just a piece of tooling that you can wind on top of. So what we're winding is carbon fiber, and so it's the inner mold, you could say, that you wind on. So think of this just big steel rod that you're winding carbon fiber to make the rocket casing, the outside of the rocket.
Wait. That makes no sense to me. So why is carbon fiber a part of the rocket casing?
Yeah, so it's essentially a pressure vessel with a hole in it, which is the end of the rocket. But
The exhaust. Yeah.
the pressure builds up quite a bit, and so you want basically in rockets you want it to be as light as possible for the stuff that isn't fuel, but you still need it to be very, very strong in terms of handling the pressure, because the pressure is very
So
high on the inside.
you have a container that's holding the propellant, let's call it.
Yep. Mm-hmm.
And that container is under enormous stress. So even if the container is like, say, a steel or something, you're going to wrap that steel with carbon fiber to add support?
No, the mandrel comes out, and all you're left with is carbon fiber. So it's just a mold.
Oh, so the mandrel's like the thing you wrap around.
Right.
It's like the mold.
Yeah, because the carbon fiber.
How do you get it out?
Good point. So traditionally, the way you do it is they're like puzzle pieces. And so you would go in and pull a piece out and pull another piece out, and they interlock and they all bolt together, right? And so it's a very time-consuming, well, not necessarily time-consuming, but it's building that is time-consuming. But you would take them in and out, so they can be reused. They're very high tolerance, and they can be reused, thousands of times. What Smart Demo is looking into is doing a mandrel, so having a steel rod that's not what you wind on, but having another material that you can essentially wash out. So it's still strong enough that you can wind on, but you can hose it out and it washes away.
And it dissolves away. It dissolves away.
Yeah.
But
Okay.
it's steel. But it's
No.
steel?
This is a second
No.
layer.
So you have a steel rod that you compact this other material on, and then you wrap on that, and then that other material, the secondary material, you can wash out.
So the other material is it's like foam? Or no, it's got to be stronger than foam, but it's something that fills up the entire space. It's not like it's not like a structure. It's just like the entire space is full.
Yep. Yeah, so that's one thing that can make us be able to move much faster. So rather than taking a whole year just to wind or to get the part that you then wind the case on, you can do it in basically a month, from like when you know what you're going to build to getting the part in, machining it, and then wrapping on top of this mandrel, washable mandrel, you could call it. So that's one cool technology that we're using that makes it so we can design, build, and then static fire within a year, which usually took us, 2 years, sometimes 3 years to get to that point in the past. And then we're also trying to do it much cheaper, which is hard, but yeah.
What kind of things, like you mentioned that solid rockets have been around for a long time,
Uh-huh.
and uh, what kind of things, I don't know what you can talk about, but what kind of things are you guys testing for?
Yeah.
Is it like grain chemistry, or is it geometry of the grains, or is it nozzle geometry? Like what kind of things are you guys looking for?
Mostly it's the materials we're using. So in traditional solid rockets that are used for defense, so we're talking military stuff, they don't want to change things, right? Because they want to know when you push that button, that rocket is going to work perfectly.
High reliability is
Yes,
the focus.
extremely high reliability, especially
Yep.
if it's got a nuclear bomb on the tip of it, right?
Yep.
You want that thing to,
Not go off while it's near you.
right, yeah, you want it to work reliably every single time. So the government is very de-incentivized to try out new things. So we call like technology readiness level is a metric, a measurement of if something is ready to be used in production. And you have several steps. So like you have the initial experiment at subscale, not in the environment you want to do it in, to see if it works. Like, will this work at all? Sure. And then you make it a little bigger, and then you make it a little bigger, and then you put it in kind of the same environment. And there's this, what we call the valley of death, where often things get through to, technology readiness level 5, but to be on-ramped onto a product, typically you have to get to 7 or 8 for the government to say, yes, like we're willing to take a chance on this. And so from 5 to 7, you basically need to show something at scale and the same environments. And so Northrop is willing to front the cash to do the research and test these new materials, these new processes to say, hey, look, we tested it in the actual environment that it's going to see, at the size that we would typically make them in the processes we would typically use, and it worked. And so that's what we're looking at. We want to on-ramp either cheaper or better or newer materials that are used to make parts of these rockets, or new processes. So we're looking at some additive manufacturing metal processes.
Cool.
So both aluminum and titanium. We've been looking at. There's some different materials in the nozzle and in the case that we've been looking at. There's different geometries, within the we call it the grain, so the shape of the solid propellant. So it's not just a single cylinder. There's typically a hole down the center, which then gets you different thrust profiles. And so rather than burning from the end forward, it burns from the center out. And if you put slots in there, then it will do a different shape, and you'll give different thrust curves. So it might be really fast and then kind of die off as you come through your maximum dynamic pressure or something like that.
So when you first were talking about the mandrel, I wasn't thinking about the mandrel for the casings. I was thinking about the mandrel for casting the fuel cells.
Yeah, and that's the other one that takes forever to get.
Right.
So that one we're looking at 3D printed. So when you think of 3D printed plastics, they're usually think of like PLA or ABS, which is not very tough. But 3D printing has come a long ways, and they actually have like they have stuff you can have carbon fiber in, or just really tough, um, what would I say?
Well,
Not
like
pro.
the chemical structure is really strong.
Yeah,
It's the kind of plastic is different. Yeah.
yeah. So it's a different plastic that they could still extrude through a 3D printer, and so we've been using that to create some of these pieces so we don't have to wait so long to form that inner grain.
So let me think about this. Do you have to, for solid rocket motors, let's say it's as tall as a house. Do you create that substance, the propellant, in sections and then stack them on top of each other, or do you have to pour it or
yeah,
compose that stuff all in one go?
yeah. So typically, for the size that Smart Demo was doing, which I would call a medium or a small, probably more on the smaller side, but it's still big. It's like, you know, a couple feet, probably like 2.5 feet wide or so.
Mm-hmm.
I'm trying to think. Diameter, yeah, 2 or 3 feet. And so there's a lot of propellant there. Those ones, I think they do just one giant mix bowl, like 600 gallons or something on that size. And so they'll mix all the propellant constituents together in a very controlled process. And
Jeez.
then they typically put the motor down in a pit, and then they'll bring a truck will bring the bowl in, attach it to a crane. It comes over, and then they hook it up, and it is gravity fed down, and then they have some ways of controlling how fast it is dropped down in, so that you don't get
And
air.
then does it cure essentially
Yeah.
is what
So
happens?
yeah, the binder, as it's called, the thing that makes the propellant and the oxidizer stick together and be hard, um, that goes through a curing process. So it's heated, almost like carbon fiber, where you have the resin that's you need to heat up. In some cases, this goes through a similar process where you basically bake it over, a couple days or something, and then it comes
That's
out
what
solid.
makes it solid.
Yep.
That's what
Hmm.
makes it solid.
Yeah.
Initially, it's just like a slurry of some sort.
Is
Hmm.
it
Is
baked
and
vertically?
Yeah. They bake it
Yeah.
vertically, and sometimes under pressure to get the voids out.
And that's
dang,
for a
it's
motor that's like 2 or 3 feet wide and how tall?
Oh,
Like at what point do you do the grains in
16.
separate sections? 16 feet?
Yeah. Well, the Gem 63 XL is what, like 30 feet long or something,
And that's
and
a
that's a
single grain?
single
Single.
monolithic case, and so they'll cast that. I think the pits are pretty low, obviously like 30 feet or something. Um, but yeah, Space Shuttle is those ones is where they started casting them in segments, and they
What?
do. There are some, so like the Gem 63, I think has multiple pores, multiple bowls, and
Uh-huh.
they do have to worry about the line where the two pores meet.
Well, that's what
yeah.
I've.
If there's like,
Yeah.
is there like an air gap would be bad,
Uh,
right? Like
yeah, any air gaps would be very, very bad. So the rockets are typically non-destructively tested, like X-ray. They take a look at them to make sure there's nothing inside that's too big, holes or foreign debris.
So, David, there is a great channel on YouTube called BPS Space. Have you come
Yes.
across BPS Space yet?
I've never seen BPS space. I didn't
Let
even
me
know
let
that
me
smart demo was a
apologize.
thing.
Let me apologize in advance for telling you about BPS Space. Anyways, Joe Barnard is this awesome self-taught engineer that's been building his own rockets for the last 8 or 10 years or
Scares
something.
me every time I see him pouring that
Oh,
stuff.
dude, there's a
And
picture of him pouring it down his thing, like in his
yeah,
garage.
he
He's like
has
pouring the. Oh,
he is
jeez.
building, he's right now working on a space shot, a 2-stage space shot, and he's building everything himself for the motor, including the chemistry of the propellant. He's done a ton of different mixing. He started with like a recipe that already existed. He has iterated on it several times, done a lot of small scale burns. He's come up with his own formula, and now he's scaling up the whole process until he can build this 2-stage space shot, right? Get a rocket up above 100 kilometers. Anyways, whenever Nate and I talk about these processes, it's Joe Barnard's videos. It's BPS Space that I'm thinking about, because he shows you the whole process. It's obviously like smaller scale, but it's the whole process, and it's
very
great.
similar to what we do.
Well, he's even got, this is not just like your like rockets you can buy at Radio Shack or whatever in the day. Like he's got thrust vectoring mounts here where he's actually, cool.
His channel started with him trying to land a rocket like SpaceX.
Okay, I have seen that. I have seen that time-lapse video. I have seen that, but I didn't know he was doing something past that.
Yeah, no, he's still going strong, doing great work. But in the last year, as he's been developing, working up for his space shot, he's been showing the tests and the formula development and the casting of these larger motors, and it's been fun to watch.
He's really cool.
Dude, I'm totally gonna lose some time on this.
I imagine
it's terrifying because he might blow up his shop, right? Is that the main issue?
Yep.
Yeah.
Yeah, there have been not numerous, but there have been a few pretty high profile incidents both at Northrop and other previous companies in Aerojet where, basically one little thing drops in the mix bowl and blows up the whole building type thing. So it's not something to mess around with.
Do you like cringe when you watch his videos? Are you just sitting there, or is it?
I cringe. I'm just like, oh man, I know it's smaller, portions, but
he seems to be pretty clued into safety.
But hold on, just pause on this. So he's pouring this thing. It's like on his freaking homepage. He's pouring this massive gray goo down into this like channel thing, and obviously there's like some rod or something down there that creates that center spot that you were talking about.
Yep.
Okay, the mandrel. But he's pouring this in this liquefied, like it looks like kind of like the consistency of mud. In this liquefied state, is it like flammable? Like that could light off?
Yeah.
So 100%. When does it become not flammable? Once it's cured, then it becomes
always
safe?
Flammable, right? Because you have an oxidizer mixed with the fuel. So once you get those two together, it's ready to go.
Anytime.
Yep. Once it's mixed, ready to go. So if that comes, static electricity is a big thing because Utah is so dry. Static electricity is a big thing where that could, if you built up enough static electricity, you could actually start to break down the propellant and it could light.
So if the propellant lights, how does it light? Is it just like burning like like on the surface? Or is it like or is it like boom light?
No. So the whole point of a solid rocket is it's a very controlled burn, right? So it's not what's the technical term? Conflagration. It's not an explosion. They don't use up all the propellant instantly like a bomb. It just will burn at a very steady rate. And so if you pressurize that, obviously that will create something that explodes. But if you just set it out and lit it on fire, it would start burning and it wouldn't stop till it was all gone. Right? There's no way to put out. Well, there are some very clever ways to put them out, but you'd have to be able to remove the energy faster than the chemical reaction was happening, right? And so you need something very, very cold with a lot of heat mass, I guess, ability to absorb the heat.
Yeah. Okay, sorry for that. Yeah. This is great, Sam. You've just totally.
But overall, the propellant is very stable. I mean, it's
It's not
not
going to
like,
go off on its own.
yeah, it's not like you touch it and it explodes, right? It's not like nitroglycerin. It's very stable. I mean, these things are handled. People have to go in and trim stuff, so they're using cutting tools, and it's mainly they just need to use the right precautions. Um, so that's the other thing. It's fairly stable, but once it goes, there's very little you can do to stop it.
Okay, so now you've got me wondering. And the space shuttle, when they were putting those the cylinders on top of another
Yeah.
cylinder on top of another, are they like machining that surface so perfectly flat so that it comes together and it just like, or are they putting
No,
some kind of chemical in there to glue it, or?
they have inhibitors is what they're called. So I'm not sure what the material is, but if you look there, I'm sure there's some pictures of just the stages. You'll see these black things on the ends, and that keeps it so as it burns out, it doesn't get into the crevice there and burn that area when it's not supposed to. And so those inhibitors stick together and are tight enough that the flame won't go up in between them. And
Okay,
so,
It's
so it's
like a big
burning. It's
flat O-ring,
yeah, it's
but
like a big giant flat O-ring that's not going to burn. And so when you stick the two together, they're only going to burn outwards, not up through the joints
yeah. So
where they come
it's like a
together.
gasket, like a flat. Think of a washer, and it fills in this space.
But when it's burning on the, like, say, the top section and the exhaust is below, and it's burning on this section too. Oh, I guess there's still pressure, so it pushes down through the center of that
Hmm.
gasket.
Yeah,
And so, wow, so you've got like sections of different fire in each one of those all burning
yeah.
at the same time,
It's
pushing.
really cool
Dang.
how they even get it started. So think of like this is what I didn't realize. If you look at a cross section of the space shuttle boosters, you've got a tiny little pellet cup is what they call it, but it has stuff that'll basically burn very, very fast and hot and shoot out a lot of hot gas fire. Um, Not instantaneously, but almost. And then that starts the initiator, which is think of like a tiny little rocket motor that shoots out to a bigger rocket motor that then shoots a flame all the way down, the end, so that the whole thing can start up in like less than a
I
second.
did not know that.
Yeah.
That's
So it lights every section, that whole
Yeah.
canister lights up at the same time.
so you get an
Oh,
even
well,
burn from the
roughly,
center
yeah.
out.
Hmm.
I know roughly, but like
Yeah.
for us, yeah, it's like probably like microseconds different, but like that's amazing.
Yeah. It's super cool how they figured that out. So you light the whole surface at the same time.
Wow.
Mm.
Okay, you've just been answering my questions, but this is very fascinating to me, so I
This
appreciate
has
it.
been great.
No, this is fun.
Okay, so one of the things I was thinking about is from your guys' standpoint, I guess Northrop, do you guys do any manned space stuff? I guess you build boosters um for Tony or Tori Bruno. What's his
Yeah. Yeah, Tori Bruno for United Launch Alliance.
United Launch that you
Yeah,
all
that's what the GEM 63 and 63 XL for the Atlas 5. We just launched one a couple days ago. It had, I think, 5 solid boosters on it, and then the Vulcan, which can do 1 to 6, I think, boosters, depending
Yep.
upon the configuration.
Okay. So you guys do the manned stuff or can do
Well, commercial
I guess commercial stuff.
and manned, because SLS, this next one will be
SLS is
manned. Yeah.
right.
That's a little bit harder because you got to make sure the accelerations don't
Damage
jiggle a
the
person
humans.
to death. Yeah, don't damage the humans.
Yep. So what's harder to qualify? The solid rocket motors for human space flight or like
Yeah.
this highly reliable thing for an ICBM?
Hmm. Um. That's kind of hard to say because NASA is its own thing. Like specifically the manned space flight because of the Space Shuttle Challenger and Columbia, issues. They're very careful, and it's different. NASA actually owns the design, and they have design authority, which is different than how most things are made for like commercial stuff. Commercial stuff, the company makes it, and you say, "Hey, I want to buy that product." You don't really get to influence the design. NASA says, "We're going to pay you to figure this out, but we get the final say on how things are done." And so there's a lot more involvement, oversight, and just checking and checking and checking to make sure things are good. So in terms of like amounts of paperwork and time, NASA with is definitely much more difficult to get something man rated. And I think there's a lot more um, testing. So I think for SLS, I think they had just multiple static tests, and typically uh, for ICBM, I don't know, but what I've seen on commercial stuff, they don't do a lot of static tests because those are super expensive.
Yep.
Okay, I'm looking at this BPS space video right now, and it's cool.
But yeah, I've actually learned
So
lots from his videos because it's kind of hard to get access to some of the stuff, you know. As a systems engineer, we're not necessarily needed on the floor, and so I have to be proactive about going and seeing everything in the processes. And some of them are, um, FOD sensitive. FOD is foreign material and debris.
Got to go through a clean room
Yeah.
experience.
So those, type of things we don't get exposed to very much. But seeing BPS space where he just chops one in half and it's like, hey, look at my nozzle. Isn't this cool? And I'm like, oh, this is so cool. I should read more reports.
Well, he's like mixing it with industrial like bakery equipment and stuff. Like
we were talking
so
about. We were talking about like setting off the fuel. When he first got those mixers, there was a video where he had to grind down the paddles to make sure that the paddles didn't come in contact with the bowls.
Yes. So scary. So scary. I'm like, oh my gosh.
So
one little spark.
He went through this whole process to make sure that there was no possible way for the paddle to come in contact with the bowl. And anyways.
How does he clean it out? Anyway, I have so many questions, but I want to ask another question.
Squeegee it out.
Just squeegee it out? Is that it? Okay, I've not seen any of this. I want to, okay, so NASA's very conservative, and I don't want you to get, you don't need to speak negatively about anyone, but Elon Musk famously is, move fast and break things kind of vibe.
Yeah.
And, but he's not, in some sense, he's not subject when he's moving, like, say, satellites into space. That's different than if he's moving people. I remember watching him on the first Dragon flight, first human to space on top of a Falcon 9 or whatever it was. Like, he was so nervous, And do you feel like there's like the extra caution is worth it? Because I mean, Elon Musk seemed to make it happen, even though he's sweating bullets,
Yeah.
But like, what is the like? Does it pay to be like ultra conservative, or is this like middle ground that Elon Musk seems to be like striking, or is he just lucky and he's just like super maverick and like lucky that Dragon turned out well and he's got enough reps on Dragon 9 so he's like it's fine? Like, what's your perspective on all that?
I think, he's definitely got the vision to and drive to like push the team, and I think he has an awesome team as well, and he's set up for success, like how he operates, right? He's got a philosophy and he's driving forward with it. Um, one thing that Northrop Grumman has specifically at Promontory is we have scar tissue, right? Like The Challenger disaster was because of our products, essentially, right? And so there are, I don't know if there are any people now, but there are some people when I started that were there that were either hired right before or right after that. And man, um, that I you just can't. I don't understand how it affects people, but you could tell it did affect, and those people were careful and methodical about what they did, right? And they do take that extra time. Same thing with NASA. Um, a lot of the same people that were on Space Shuttle, that team went on to do SLS, and so they have that scar tissue as well. I don't think Elon's, SpaceX's folks, obviously, a lot of them are very young and don't have that. Not saying they're reckless. Um, I I think their philosophy obviously works, and there's um, contractual differences between the way they operate. Like SLS was a cost plus uh, contract, which meant when NASA said, "Hey, we want you to do something," we said we would love to because we get paid and the company gets profit. And so, it was just sure. There's no reason to say no. SLS is different. They have contract awards for meeting things on time and staying under budget on things. And so there's a different philosophy with that. And then of course SpaceX, they are like very profit driven. So they are trying to minimize all of their costs as much as possible, right? And their contract with NASA is very different than. So NASA didn't. I don't think NASA had direct design authority. They just said, "Hey, we'll give you this much money. Go make your thing." And by this point, you have to be able to deliver a product that will get stuff up to the space station, which they did. Um, so that I don't know. I think there should be a healthy middle ground. Like you should, you know, understand, and that's one reason why the astronauts come around. So we've had astronauts come to the plant and tour the plant and talk to everybody. And once you put a face to who you're putting up there, like, hey, the thing we're making, that person's sitting on top of. If we mess up, that person dies. That's a hard thing, to have to deal with.
So
So that's kind of my thoughts on it. I don't really know if one's better than the other per se, but
I'm not sure the question's the right question. Meaning, NASA oversaw the certification of Falcon 9 for human flight, human rating, and the same organization that qualifies SLS qualified the Falcon 9. So the thing that's in some ways different than, like, if you go back to the Saturn V development or even before that, the early rocket developments, the thing that was different is, like, you needed a human on board to do the flight test. Like, like for some of those things, right, you needed the human, and so there was like this immense amount of risk. But these days we have such sophisticated computers. If you look at the development of Falcon 9 or today's Starship, they can build fast, move fast and break things, because there doesn't have to be a human on board. We can lose as many rockets as we want for the purposes of education, because there is no human on board. And with the Falcon 9, they didn't go and like, they were able to get the human rating for Falcon 9 based on, it was like 150 flights or something. 150 like successful flights of Falcon 9 with huge amounts of data around like the thrust profile and the G loading and all these things, right? And it was only after all of that,
and the reliability of everything,
and all of the before they put humans on it. SLS is a different beast. They went at it in the somewhat traditional way, where like huge amount of analysis, huge amount of like simulation, one test flight, or maybe 2 test flights, I don't remember.
One.
And then was it one? And then we
Yes.
went straight to the human flight. So, but at the end, NASA was the one who certified both vehicles for human flight. So yeah, I guess maybe it's like both ways work. Yeah, and then you also, in more recent news, you look at Blue. You look at Blue. What are they called?
Blue Origin. Yeah.
They took a more traditional approach. Massive amounts of analysis, years of design and simulation,
and they stick the landing.
One test flight, and then they stick the landing. And so they obviously both work as far as design philosophies.
It'll be really interesting to see. Well, I guess they got to orbit with their big one, so they kind of won in that sense.
Who's
but
that?
We'll see. Well,
Blue Origin.
For Blue Origin, right? They got a payload up into orbit, whereas SpaceX has yet to get a payload, an actual payload up with their ship.
Yeah.
But that's not necessarily their goal. They're trying to get it fully reusable, get all the kinks worked out, and then they'll just start pumping them out.
Yeah, I'm just very much team space on this thing. Like we don't need to be like Blue Origin is doing amazing things. Their vehicle is incredible. It's like between Falcon 9 and Starship. Starship is going to be an incredible platform. They're focused on a very different thing than Blue Origin right now in terms of their development cycle and their development approach.
Well, he's focused on Mars. I mean, he's focused on, Moon is like, well, whatever. Just like, we got to get tonnage to Mars. That's like a very different kind of perspective in my view.
Yeah.
Then like Blue Origin is like, hey, we're going to be in this great place and we'll put up another Kuiper network and it'll be awesome. And we'll get a lot of tons to orbit. That's very different. It's a very different set of design criteria.
Did you guys see the announcement of SpaceX IPO next year?
Did. Man, I don't know. It will be interesting to see how that goes out. IPOs can be so tricky. They can sound great and then like it just benefits a few people, but the guy needs to raise money, so he's like, hey, this works. I don't know. I wish him luck.
He's raising money to put data centers in space, which I think is one of the dumbest things ever.
Okay, why do you think it's so dumb? Hey, he's totally into the solar panel stuff. He's like, it's free energy from this nuclear reactor in the sky. There's no weather to deal with. It's going to be charged 24/7. What's the problem, Sam?
Heat. The advantage you get for energy, high amounts of energy, you generate a massive amount of heat and there's nowhere to put it. Because in a vacuum,
I guess space is kind of cold, right? Like,
no,
is that a problem?
But you can't convect or conduct heat away. The only way to get rid of heat in space is radiation. And it's not a very effective process to radiate the heat out. So like space is we perceive it as cold, but it's not cold in the way that we feel the air is cold around us. Right? So you can't just like put a heat sink into space and like convect or conduct heat away. You have to radiate it away. And it's not a simple problem to solve. So I just you solve this problem of energy, and then you have to you accept this other massive problem of like, what do we do with this incredible amount of heat that the data center is producing? Obviously, Elon thinks there's a solution for this. I'm fascinated to see what these what these radiators are going to look like, because getting rid of heat in space is a challenge.
I didn't know it was specifically for I did read about that, but I didn't know that the IPO was specifically for that. That's crazy.
That's what I read. I don't know. I think it's wild. I'm also concerned because Musk has said for a long time that he kept the company private so that he could focus on the vision. And I'm concerned that like if he makes it public and he loses control and SpaceX,
I don't think there's any chance of
vision.
Yeah, I don't think there's any chance of him doing anything to lose control. I think he's pretty focused on that. Okay, Nate, you're a rocket scientist. You get that at dinner parties. That's pretty awesome.
It's always what my dad calls me. He's like, my son, the rocket scientist. And I'm like, I still don't really feel like that, but okay.
What's your take on a new NASA appointment? Isaac's like there's a little bit of drama there,
Yeah.
but my like armchair quarterback perspective is like this is a great thing. I was really sad when he kind of like got on the outs and didn't get the appointment, but now he's got it back in, and
Yeah.
it looks like I mean I listened to an interview. It's Isaac Men, right? Isaac or Isaac's son? What
Jared
is it?
Isaacman.
Isaacman. Okay, yeah.
Yeah.
I had it right the first time. Anyway, he seems super sharp, super like I think he
Yeah.
understands stuff really well. But sometimes people I look on the outside, but then when you're on the inside, it's like, nah, actually there's some issues here. What's your perspective on him?
Excited about it. I was just talking to my wife about this on, he's a successful businessman. He's a pilot. He's an astronaut. Um, he he's a good leader, it seems like, and I think he is very. At least the sense I get from him is he's pretty like down the middle of the road. He's like, hey,
Not
we want to help NASA and provide vision, but at the same time, um, you know, not like go crazy with it, but like, just I guess make it good again as kind of, maybe not again, but I don't know. I need to dig in more to what he's actually said. Like what I do wonder, like, okay, there's been a lot of changes, and I'm sure a lot of people that work for NASA are kind of like, oh, what's going to happen now, and how they're going to reorganize, and what the vision will be for them. And I think it'll be nice because I think he will have a clear vision and be able to help everybody to see that, um, and kind of dispel this confusion and chaos is what I perceive. So those are my thoughts on it. I need to dig in more because I don't know his background very well, but that's from the outskirts what I see.
well, that's super fair. So you and Sam follow this stuff so much. I'm kind of a SpaceX fanboy. I appreciate the diplomatic way that Sam's like all good space stuff. We want all of the things, but like I really like what SpaceX is doing. It's exciting to me to think about getting on the moon with that big vehicle, and also seeing what we can do at Mars. I think both of those things are really exciting for me. But since I'm an outsider, what are the like super cool things that you see on the inside of this like industry where you're like, actually the cool stuff's over here or over here,
Yeah.
or like what is the
Oh
stuff that
man,
like is exciting for you?
just the fact that there's so many people working on this, um, it really is the the second golden age of aerospace, of rocketry. Like, and the other cool thing is like, so I follow Scott Manley, who does like I don't know if it's monthly or weekly, but he does a deep space review, and he goes through literally every launch on the planet. So you get a bunch from Russia, you get a bunch from China. Occasionally there's like India or France or Australia, and it's hard to get news on China on like what they're launching, but man, they launch a lot of stuff. And I didn't realize this, like they have a freaking awesome space station sitting up there, that I didn't even know about for a long time, and they're pushing to go to the moon. We'll see who gets there first. The other thing that I'm really
We did. We got there
stoked
first.
about, yes, we did.
But did we,
Sorry.
Sam? Did we? Did we?
Oh no!
We
Don't
did.
you dare start
Oh
that.
gosh.
The other thing is it's Stoke Aerospace, right, Sam? That's doing the
I
reusable.
love
I'm
they're doing amazing
stoked
things.
about Stoked Aerospace because
Oh, they're doing
What are they
amazing
doing?
things.
What's so cool about what they're doing?
so they started with, they wanted to make their second stage. So the thing that actually goes up into space they wanted to make that reusable. So
That's
SpaceX
the
is
hard
doing
thing.
that with Starship. They have the Starship that comes down and does its belly flop maneuver and has the fins and comes down. They're doing a totally different thing. It kind of looks like a traditional capsule, but it has this heat shield that they pump the cryogenic fuel through. And so
That's how it keeps cool.
yeah, and so some anecdote that I heard was they're not worried about the heat shield being too hot when it gets to Earth. They're worried about it being too cold because they're flowing all this cold, fuel through it. But the other cool thing is if it springs a leak, it it actually what is it? Not a positive failure, but basically it fails safe, meaning if it springs a leak, it'll actually put a cushion of this cryogenic fuel out and will protect it. And so I want to see that work. That's going to be
Well,
I
that's
just
isn't
jump
that
in here? Wait, hold on.
okay? Okay, Sam.
This
Okay, Sam.
project
Tell us the
is
deal.
so cool.
yeah.
Because okay, you see, Elon Musk is constantly talking about the heat shield. He's constantly talking about how hard it is. He's talking about like, we're going to be solving heat shield for the next few years, whatever, right? What Stoke has done is they're solving that first in a super significant way. So it's more like a capsule, with an oblong shape for control, just like, a capsule from the moon, project. And they don't need heat shields because they're doing this, auto regen. They're using fuel to cool the heat shield. And if they can figure this out, they have a smaller surface to cool. They're able to cool it without a heat shield. They get a fully reusable second stage, which is the holy grail. And I love that they're like solving that problem first in a super meaningful, super creative way. And then they're going to build like a first stage and go to space and have an incredible platform.
Yeah.
It's
the giant Pac-Man.
Yes. It's going to be amazing. And I love what they're doing. They're solving the hardest problem first, and they're doing it what appears to be in a really great way.
So the videos I've seen, it's got this ring around it. Is that ring is that the fuel coming into the atmosphere, or is it just through these channels that are like probably 3D printed or etched underneath the heat shield? How does this work?
The ring is the engine, so there's like a bunch of little tiny nozzles that together work as a single engine essentially. And then I think it's underneath they have channels that do the fuel is what I would
So the
assume.
engines are just attitudinal control? Is that all those are? Because they can't, those engines don't look big enough to launch the thing.
I think they are. Yeah.
Well, it's a second stage. It's not to launch it off the ground.
So they're already up. Okay.
Yeah, they're already boosted. But those are the second stage motors. It's one motor with like 10 different thrust chambers.
Exhausts. Yeah.
And then that's what gets them to space.
Yeah, it's really cool. And it's kind of like a what's it called? What did Dr. Whitmore love? That I'm I forgot what it is. Do you remember what it is, Sam? So it's rather than having your nozzle like this, you flip it like this.
Oh, it's a aerospike. Yeah.
It's kind of aerospike-ish in a way, just because they don't have like a traditional huge nozzle expanding out. It kind of expands along the trajectory or the profile of
the aerospike. That effect allows them to get higher efficiency through the different layers of the atmosphere, right? They get optimal thrust, through the upper layers of the atmosphere.
Instead of being gated by the different nozzles, have one nozzle for like low Earth orbit and another nozzle for space, vacuum of space. The aerospike just like automatically adjusts for all of that. Yeah, that's very cool. What else? Are you excited about the moon thing, or is that just kind of like whatever? We've already been there. I'm not interested.
I think it will be cool. I get questions all the time from my wife's family about this, like why are we going back to the moon and what's the point, and also why is it so hard? Like, didn't we already do this? Why did these things keep crashing?
It's
And I'm
kind
like,
of a long ways away. I mean, just
I
saying, it's a long ways away.
yeah. Well, I keep telling them, I'm like, okay, if you had $1 million to design and build a tractor, or if you had $100 to build a tractor, I mean, like $100 for a tractor that actually worked is pretty much impossible. That's kind of what they're dealing with right now is significantly less resources
That's a
to
great
do
way to
the
put it.
same thing.
Okay, that is like such a good comment because I heard this story. So Von Braun, he's a rocket scientist like you, and and he apparently had this whole like Saturn 1, 2, 3, 4, whatever. I don't know the story quite right, but he was like, okay, well, we've got it. He had it all staged out, and they like skipped 6 stages and went to like the moon. Do you remember this story? Am I like
I,
out
I
of?
haven't heard this particular part of it, but I understand the acceleration of the program. Yeah.
Yeah, yeah. And so like but I guess maybe they were just so overly capitalized that they were able to do that. That whole program blows my mind. Still to this day, it blows my mind. From a software perspective, from a like control perspective, all the things. So it feels like, hey, like we're smarter. We have more technology now. We should be able to pull this off. But I've got a neighbor down the road that's working on that the Artemis program. And which I think is that Artemis is the platform for the moon. Is that right? Or is it just the
Artemis
replacement
is
for
the
the?
Artemis is the mission. So there's several Artemis missions. Like SpaceX is part of the Artemis mission, and Space Launch System is the vehicle that NASA is doing. That's doing the first and second, and I guess the third, getting people up there. I don't even know how that mission profile works, but I know there's supposed to be 8-ish, or maybe even like 12 Artemis missions. But is it 5 now that Congress said yes to? I can't
I
remember.
don't know. It
I
was cut down. I don't know.
Yeah.
Okay, so bottom line is, you look at it. Sam's really excited about Stoke Space because he's solving the heat shield thing. Yay! But you're not really stoked about. I'm not sensing the stoked vibes about the Artemis, like SLS to the moon thing. Is that just because we're so undercapitalized? Because basically there's not enough public will to pour the money that direction, and so they're just trying to like make something really complex happen with 1/100th of the budget that they need. Is that your perspective?
Yeah, I think also there was a really clear vision with Apollo. It felt like, looking back on it, like they just everybody pushed kind of in the same direction. It seemed like, whereas now with the politics with it, they've gone through several iterations. So first it was, they called it the Constellation uh, program, which had both a manned thing that was kind of its own ship, and then something to get the cargo up, and then they axed that, and then they started back over. Now we've got SLS, but now SLS has like Starship as part of it, and these other companies, and so it's kind of like it feels kind of hodgepodged together. And I think that's because the top down to NASA is, we want you to utilize more commercial assets and get the commercial stuff going, rather than NASA, you be in charge of getting a
Doing it
contractor
yourself.
to figure it out. Yeah. So I think that's the difference. And uh, there's there's got to be some economics driving it, right? It's hard to just keep a presence on the moon when there's not like a clear benefit, I'd say, um, for people to be incentivized to do it. Like, some people
So
are
the benefit in
incentivized
the
by,
past, and the benefit in the past was the Cold War and
yeah,
American supremacy and like dominate, like we are the, but that doesn't feel like that right now
no,
so much.
there's not really a race. I can tell some people are like, we got to beat China, we got to beat China, and it's like,
Do we?
people,
Yeah, do
yeah,
we? Maybe there's a lot of gold up there. I mean, like
yeah, I don't know, but I mean, the other part of me, like the scientist part of me, there is. important discoveries that can't happen unless we push ourselves to do that, right? Um, when I used to work at the university, I used to think, man, there's all of this wasted money where people are doing all these weird science stuff, and I'm like, this has nothing to do with anything. Like, there's nothing's ever going to come up with this. And then, as I've been learning more and more about scientific discoveries, I watch a channel called Veritasium. He goes through a lot of like, here's how this scientist discovered this or figured this out. A lot of it is by happenstance. Like they weren't even trying to do this. They were just messing around and wabam, they figured something out that helped everybody, right? Not always does it happen that way. And so I've kind of changed my thinking about it to there does need to be basically a slush fund to give to people to say, we want you to try crazy ideas that may not on the surface have any link to anything useful, but by doing that, something will come of it because in the past, that's how discoveries have been made. And science needs that freedom to just mess around and try stuff to then get to the discoveries that do help us. And if you constrain it too much, I think that kills that ability.
Fascinating. It's a great perspective. Tell me about one more thing that like is going on in the space energy that just like obviously super stoked about like this new golden age. Everyone's doing it. It's like the billionaire hobby, I guess.
Yeah.
Like what else is like exciting for you?
I am, well, this isn't space, this is more aerospace, but Boom Aerospace getting back into the supersonic
Oh,
air stuff.
love
I'm
it.
like, yes, bring it
More
back,
of that,
baby.
please.
Yeah,
More of
like
that.
let's figure it out. You guys gave up way too soon, you know. There's got to be a way to get the economics and physics to align. And just hypersonics in general, you know, back in the 60s and 70s it was around, and we kind of just pushed it to the side because there wasn't really a use case, and it was expensive and hard. And now that other countries have figured it out, you know, we're coming back into it and really figuring this stuff out. And I'm excited to see what, you know, comes out of that. It's very, very interesting.
Nate, did you see Boom's announcement from last week or the week before?
No, I didn't see
They
that.
announced that they're taking the Overture. So they've developed the motor, the jet engine. It's all custom. It's high performance, whatever. And they're making it into a generator, a natural gas generator.
Oh, okay.
To provide power to these AI data centers that are, you know, in severe need of power. And
interesting.
I think it is interesting. Like, anyway, so they're talking about like, look, we have this incredible motor that we've developed, and we're just gonna take that same motor and hook it up to a generator and produce high efficiency power for these data centers. A whole new product line.
That is super smart. Honestly, like I didn't know they did that, but I give them full marks for that move.
Yeah, that's like what Cat does with their huge diesel engines, right? They emergency backup generators.
I just think that's fascinating because I like the capex going after energy gen right now, especially in the US, is just astronomical. Like we've never seen anything like this before, and I that's gonna create a lot of money that will allow them to, if they want to, keep working on the hypersonic stuff. It's not hypersonic, it's supersonic. Yeah.
I think they're very committed to that, and the supersonic transportation side of things.
No, I think they are too. But like they could get, you know, they start making a lot of money on this because there's a lot of data centers that need a lot of power, and we don't got nothing, and we have no transmission and no nuclear and just all the problems that everyone knows about. Then I mean, and we do happen to have a lot of natural gas, and so until we figure out nuclear or some kind of solar battery thing, then this is going to be, you know, this is going to provide a lot of runway for them. That's exciting. That's super exciting.
All right, Nate, we're a little bit away from the technical side of things. As you look back, you know, you've been in industry 12 years or something like that. I don't know, 10 years. Um, what advice would you give to, you know, undergraduates at Aggie Air today, right? That are just like, that's Aggie Air is where Nate and I met developing UAV platforms for remote sensing research, right? Young
Yeah.
and dumb, we were just like building stuff and learning. What advice do you give to those guys as they, finish up their degree and are looking towards the workforce?
Yeah. Well, hopefully I would intercept them a little earlier and say, build something. Like
Really?
yes, just
What?
build anything. There are so many engineers that come out of school that have not built something. Just
Okay, why? Why? I want to pull on this thread. Why is that so crucial?
until you go through the process of actually building with your own hands something, you cannot internalize um, those steps and like that thinking process. So there was a lot of the best people that we hired at Aguirre were people who had done their own coding, built their own cars, built their own airplanes, or had hands-on practice at building something that they got to work. And that process cannot be taught in classes. It has to be learned with your hands, right?
Why is that? Why can't you like go through the motions of like, hey, well, this is how you build something. I mean, I watch a lot of YouTube
Yeah,
videos. There's like these YouTube videos of these builders building these cars and crazy things, and now I'm
yeah.
gonna watch this one about
It,
rockets.
it's
Like, what's the difference there? What's going on? What do
I
you think it is?
it's the same thing with like when I watch a YouTube video, I watch like 10 different ones on how to fix my car, right? And I go out there and I'm like, okay, I got this part, and then I'm like, heh, and I'm like, it's a little different, and like, oh, what did, how did they get this in there? Like, you can't get that unless it's the 3D physical world, right? You can't get the same perspective. But also, I think it's just there's not we refer to it as scar tissue. You didn't go through the process and experience the pain, and it's the same thing in life. The best way to learn something is by doing it, right? Like doing the thing and failing, learning the lesson. That's the strongest. Like it just is deep into your mind. Whereas for me, a lot of the things I learned, I didn't know how to apply. Like that's why math was hard for me. I'm like, I don't get how this fits into what I want to do, right? And so building something, you can take those pieces that you're learning or eventually will learn and apply them back to, hey, had I known this, I would have done this to start with, or oh, I can see how that fits in here. But if you don't have that underlying skeleton of knowledge, it's really hard to like fit the pieces together, I would say.
Do you think there's a do you I wonder do you think there's a portion of that? You call it scar tissue, is a really interesting idea, but like, is you think part of it is a humility to the process? Like, things are really a lot more complicated than you think when you actually try to do them. Like,
Oh
is
yeah.
that part of it as well?
Mm, not necessarily the humility, but knowing what questions to ask. Like if you've never done it, you don't even know what questions to start asking. So you just start doing it and you keep messing up and messing up and messing up. Once you go through that, when it comes again, you kind of know what questions to be asking at the beginning to figure out in which order. The other thing I would suggest is an idea of always learning. Um, this is something that I'm trying to practice, and I think it's I feel it like part of my job is to just always learn. The moment I stop learning, I'm no longer a useful tool, right? And I've seen this especially in systems engineering because since I started, there's an emergence of model-based systems engineering, which is basically just using a computer to develop a model that represents something you're working with to make those relationships um, so that you can, we call it interrogating the model, but different ways to look at it, the data to say, hey, did I get all the relationships right? And if I
Mm.
change this one, how does that affect the whole? And you need to kind of look at it from different views. Um, that is this just emerging, ever changing thing right now. Like from year to year, I mean, it's moving very fast, and so that's something like I'm going to take a class next year from a university on model-based systems engineering because I'm like I'm getting behind the curve already, and I'm
Is
at the
this
front of it, so I better be staying up on it.
Yeah, yeah, yeah. This is fascinating that you would say this because I see similarities with my, I most of my career has been as a software engineer, and all thinking of soup to nuts, different big corporations, small startups, all kinds of things like that. And I've just recently started at another startup, and this startup is so early stage that we're just like building the whole thing from scratch. And I was working with one of the other engineers. It's basically just um, there's me, this other engineer, and then a part-time of an engineer and a data scientist. Like that's like the technical team. And so very, very small, just getting off the ground. And one of the engineers made this comment to me. It was Charles, who we had on the podcast a while back. He's like, it's very, when you meet an engineer, finding an engineer who knows what it means to go from zero, from nothing, and end up with something, he's like, that is more rare than common. He made the point that like finding someone like that is really valuable because of what you're saying, that there's something that clicks in when you're like, oh, like these are all the different things that need to happen. And I never recognized that until he said it. And I never like internalized it. Maybe it's because I was living it just so much, like personally. It's just like, well, this is what you do. Like you got to find this, and you got to do like, so from most basic things to like register the domain to like setting up your DNS or getting the certificates right. So like all this like DevOps stuff that you got to do just to get the website up, and then you got to figure out how to do something that's actually valuable. Anyway, that's a very similar thing. I think there's another thing that I would say, and maybe this is just high tech or because we're all in high tech industry, right? But like this idea that you have to be constantly learning as like your superpower, like you're doing it with this model and model based thing, which I want to ask a question about. But like that idea that the I was talking to Charles about it. He said, look, every 2 years, my tech stack changes. And I was like, dude, that's totally true. That's been my career too. Like things just are constantly changing. And you're like, oh, well, the new hotness 2 years ago is now it's this and now it's this. And you don't have a choice. Like you've got to update. You've got to retool. You've got to like immerse yourself in that new thing. It's kind of exhausting in a way. So like I understand why people would avoid it. But if you're going to be in engineering, it seems like that's just like par for the course. Tell me about your this. Are you building a digital twin of your system that then when you're interrogating, like, is it like CAD CAM like digital twin, or is it like something more abstract?
It's more abstract. There is the pie in the sky of having a digital twin of everything we do, and
Yeah.
Northrop as a whole is definitely pushing for that. That's a really tough thing to have because it's just massive amounts of data and a very large model, and nobody really knows. It's very new, and so how to do that and how to link things is hard. But ours is a little more abstract. What I deal with is mostly the requirements and the verification side, the interfaces. Um, we're also looking at some of the physical architecture, meaning for this configuration, which parts do we have that fit together, and you know things like that. So that's the stuff I deal with. There is the broader model-based systems engineering, which deals with how things behave, and so doing state machines and more like almost like electrical diagrams, but saying, all right, here's this pinout, physical pinout, here's the signals that go through here, and defining stuff like that, and then you can um, link up requirements to that or verification or other things. So it's all kind of interconnected. So when you change one thing, it flags the person, oh, I'm changing this, so that has effects all throughout these other things, and I can go check on them, rather
Can you
than
give me a practical example of how you use model-based systems
yeah.
engineering?
So rather than doing a document, whether that be a digital document, and saying the rocket motor shall weigh this much, right? We have an object in this model that represents that requirement.
Mm-hmm.
And so you make that object, you give it a name, and then typically we do it in a diagram form. So just think of like almost like a PowerPoint or a logic flow, and you've got your requirement, and you say, okay, for this requirement, this it applies to this part of the rocket motor. So you say, all right, well, the case, or typically we would break that up and say, all right, now the case can only weigh this much. So we have an object that represents the case team, or the abstract version of the case. And so now we could say, all right, show me all the requirements for the case. So you could like see the links from this case object to all the requirements it needs to meet, right?
Is this some kind of specialized, this sounds like an object graph or like a knowledge graph even. Is this like some kind of specialized requirement software that NASA's like
No,
requires you to use, or is this?
this is just in general across basically everywhere that does large complex systems is starting to use. There's a few different softwares out there, but so there's like different softwares, and there's actually different languages. So there's what's OML? Object modeling language,
Yeah.
or so it's this. There's a SysML, which is system modeling language, which is based off of OML somewhat. And so it's very much an object-oriented language where you have these objects and you do certain types of links, and each object has certain properties. Some are readable, some are writable. And then when you create different types of diagrams, be it a table like a traditional Excel spreadsheet table, or um, a dependency matrix, so like think of an n by n matrix where you can say, hey, here's all these things. How do they link to all these things? And you'll see little check marks.
Mm-hmm. Mm-hmm.
And then we'll have like visual diagrams where it's like this block, you see the arrow linked to this block, and then links over to this, and there might be some over this. And so many to one to many to many linkages that you can see at the same time. Um, so, and then you can basically spit out documents if you wanted to, but then you can also link other models to it. So you could have several of these models and say, they can grab the requirements and go to some other model and do it there. So you could have the same set of requirements, but
Does it help you with like consistency checking, like where you're like, hey, this requirement is actually in conflict with this other system, and when I add this third system, then there's a triple conflict? Does it do that kind of stuff, or are you interrogating the system to try to expose problems like that?
kind of both. It's fairly new to do automated stuff, and we're trying to figure that part out of it. But we do a lot of interrogation on, you usually it's, does every requirement have at least somebody that's responsible for it? Does everything have a method for verification? And then we go through with the teams and say, okay, here's what we think you're going to do to show verification to this requirement. Is that correct or not? And then we'll update it, and then we can give them that information fairly easy from the model and say, all right, here's the stuff you're doing, here's the stuff you're doing, versus how they used to do it, which is you give them a big jumbled mess, well, not a jumbled mess, but a whole list of requirements, and then they'd kind of like by hand mark what they wanted to do, or you had a spreadsheet,
You're
or
like, Joe's got that one, yeah, Fred's got that one. Like, I mean,
yeah.
just like, oh,
And
wow.
mainly things would get out of sync. You'd have to, update this Word document. The customer would update theirs and this one,
Mm-hmm.
and then you have some other document that has the trace between the verification and this, and then you'd have some report that had those requirements, but now you've got to update these 3 things, and some things get missed, and so this
So it just
prevents
puts
a
all
lot
of
of that.
that digital. It's all
Yeah,
digital and connected so that everyone's referring to the same thing. Everything's in
yep,
sync.
One
yeah,
source of
Yeah.
truth.
yeah,
Yeah,
and
that's
that's the
nice.
big buzzword, is the source of truth. Where's the source of truth? And the ideal state is as much as possible in the model, where it makes sense, and then you have these, I'll call it a window into the model that anyone can access, and it's instantly up to date, and there's ways of locking the model so no one else can change it, and so you can configuration manage this stuff too. And so that's the ideal state. In practice, it's a lot harder to get there. We've been working on this for the whole time I've been here, and just in the last year, it's finally just this uptick of people are starting to get it. I think part of it's, um, students coming in are being taught this at school. Like, there are a ton of universities that now have systems engineering degrees, and 10 years, 20 years ago, you wouldn't even know what that is.
Hey, I have a question. That's a great description. I have a question more broadly. Yeah, AI is like definitely a force to be reckoned with in the software engineering space,
But yeah, yeah.
right? And I'm like in an AI startup right now, and so it's like very, in my face. What I get the sense sometimes that other industries may not be experiencing the kind of flux that I'm experiencing. Are you seeing AI as like a practical like force in your industry, or is it still kind of something out there in the horizon?
No, we've already. I mean, I've already been part of some co-pilots where they're like, "Hey, we can use this to check all of our requirements. It can go through, have a set of rules, and we can already tell which ones don't meet those rules. Just like boom." And we're like, "Great! Person doesn't have to comb through the whole list. You can have it do its initial check, and then do a double check, and it's going to catch most of it for you." And so we're really trying to figure out ways
Just so
that
you
we can.
know, that totally scares the crap out of me, but like, so I hope it works. Like, I
Well,
mean,
the other thing we're trying to do is,
like, if there's a rocket that's doing that system, I want to like maybe not be on it.
this is totally beta, and everything has to be checked afterwards. We haven't
Okay,
used it
there's
on
human oversight, humans in the loop.
yes.
You're right. I should not be.
Yeah, that's one of the key things, is human oversight, that the company is very, um, cognizant of, I guess.
Uh,
So
uh,
we've all had this training, and in fact, Northrop is very, um, like, was pretty quick to say, "Hey, we see this is useful. Let's figure out how to use it. Let's set up some, policies and best practices on how to implement this stuff, and let's start to figure out how to use it."
fascinating.
Well, this has been great. We have covered all of the topics I wanted to cover, and I was glad. I was going to ask about the model-based systems engineering, so I'm glad we got to that. Is there anything else, David? Any last things that you want to ask about?
No, I feel like gosh, I guess it's already been a long time, so I'm just really grateful for you taking the time for this. This has been fascinating for me. Thank you for answering all of our questions and just like being a champ.
Nate,
It's great.
any final words of wisdom?
All engineers are systems engineers, or at least they should be.
I like it. I agree with that too.
Systems engineers are a special breed of engineer. Like, if you start to talk to other people, they're like, "Uh-oh, the systems engineers are coming around. Run." That's kind
But
of,
you know what? When you were describing, here's something interesting. I will just say, Nate, when you were describing the role of a system engineer, I was internalizing. I'm like, yeah, this guy's like a product manager. And
yeah,
not the product manager in like the brand sense of the term, where you're like, managing the external things, which is kind of like where that role originally came from. But like, yeah, you're working with your subject matter experts, you're creating the solutions, you're connecting the dots, you're making sure everyone's aligned,
yep,
you own the requirements, you've got to make sure your customer's satisfied. Like all of that sounds just very,
yeah,
so I'm VP of product right now. And so that I was just like, oh yeah, this is very, this echoes like a very similar thing to me.
yeah. And another way to think about it is, very broad. We can talk to all the groups, but we're also very deep in our specific process and how to help all the other teams. We're very much like a service oriented style engineer that like our job is to help everybody else out do their jobs better and help everybody connect and
But
make sure they know what they're doing.
No direct authority. So you're needing to influence without a line of direct authority, which is exactly the PM role, right? You're trying to, none of the devs report to you, none of QA reports to you, none of engineering. Like it's just like but you're still responsible to get it all working. Yeah. It's very cool. Very cool.
Every engineer is a systems engineer. I'm a fan. Well, Nate, thanks for coming on. I appreciate you taking the time, and I thought this was great. I really enjoyed it. So this has been another episode of the Build Different podcast. Thanks for joining us. We'll see you later.
Bye-bye.